Okay, welcome to the first day of October. This is our lab 6 since we started, and this is the 6th week actually. So we've been doing one lab per week, so we never missed a beat, which is very good actually. I'm very pleased with the way that we're operating right now. Please, if you think that we're moving too fast, please let me know. I think this lab actually you're going to enjoy it more because it's actually less stuff in it. I think for the people who looked at it, they should probably have had that impression already. So we're going to talk about it. Probably it's not going to take us a long time before we finish it. And then I'm still working on Lab 7, which is due also a week from today. And again, we will see how that goes. So today's lab is about buoyancy. And again, probably you know by now basically how the process works. You're supposed to go into the lab instructions, download the file to your computer. Do not rely on the fact that it could be opened by your browser. Then right-click on the file, open it with Adobe Reader or with any Adobe, with any product that can actually save content to the Adobe Reader and submit it, okay? Once you make all the changes to it, you need to submit it after you submit it, you review it to make sure that the submittals are actually good. If you need to edit it, you're going to do the process all over again. This have been through it now for at least, this is the 6th time, so I hope that now you mastered that. Also, don't forget the rubric. The rubric actually is your guide in terms of what you need to do, because it shows you point by point, basically, how much you're going to get in this lab. If you do this, if you don't do that, if something is missing, basically. So you know exactly how the slabs are graded. So hopefully you use the rubric as your guide, basically like a check mark to use for checking that you did this, did that, this. Now I have my lab 100% ready, so I'm going to submit it and I should not have any difficulty with it. So that's basically in a nutshell in terms of the instructions on Canvas. That's all you probably are going to get from there. So today's purpose is actually go through those instructions and make sure that you guys have no problem, no difficulty doing this lab. This lab is a little different than a couple of the ones that we did. This is similar to the very first one. This uses actually GeoGebra. It doesn't use the other website, the PHET application, the PHET activities. And there is an issue with GeoGebra because resolution on your screen may matter. You might not see everything on your screen. You might have to change the resolution on your screen or probably browse in and out of the screen to see the rest of the content. For this lab, there are 2 points on the bottom. One talks about the opacity of the fluid. Ignore that. You can take the default value. Basically, with the opacity of the fluid, can you see through it to see the content? Actually, you don't need to change that at all. You don't even need to also change the viscosity, okay? At some point, I ask you probably to change it a little to see if it makes any difference. But the viscosity is for dynamic processes, basically, because it involves friction and friction involves movement. So what we're doing in this lab, so that you guys are with me on it, we're doing the case of hydrostatics, case of the fluids are stationary. And if they're not, we'll wait for them to come to stability of some sort. And you will see whenever you make a change to this fluid, for example, changing the density of the object, you will see that it goes through transition. The object is either falling into the liquid or rising from the liquid or doing something. And during that time, there is all kinds of things moving around. Once it settles down, is that when you take your reading. Don't take it while it's transitioning. Okay, so that's basically the only warning I have for this lab. Everything else should be straightforward. You're going to be changing the density of the object to make it look like it's that of the wood, which is about 0.5 basically grams per cubic centimeter. And then you're going to change the density to almost that of an ice. The ice is 0.94 or 934 to be more specific, which is actually closer to 0.95 because the increments in here in density are by 0.05. So you need to bring it to as close as possible from the object, so namely the ice. And again, you're going to make observations based on that. And at some point, I think you're going to do iron, which is 7.87, which is very close from 8 grams per cubic centimeter. And basically, that's in a nutshell what it is. And then at some point, you're going to change the fluid from that of water, whose density is 1 gram per cubic centimeter, and change it to a much, much more denser fluid, and see what that will do, okay? Add a lot of salt in if that's what you want to think about, okay? And it stays fluid, but it's very, very thick in terms of density, and see what happens in terms of the same objects that you were analyzing. So this is in a nutshell what the lab is, okay? So the whole thing is on, again, buoyancy. So let me go back into the instructions in here, so the ones I'm sharing with you guys. Again, do not forget to include your name. That's very important, and the name of everybody who worked with you. So if you find similar statements and the name of the person is not there, I'm kind of a little bit suspicious at that point that you really did not do something in here, okay? So you will lose points in here. So if you honestly work with somebody else, just put their name in there. You're not going to lose any points. As a matter of fact, that's good. That's what I want to see, okay? Again, this is the theory. I know we talked about it from in class today for Physics 10. If you didn't take Physics 10, this is actually a good point in here. If you didn't take Physics 10 today, it's a good thing to actually go through it and review these things and understand basically what the buoyant force is, what is Archimedes Principle, and when will objects sink or float, okay? And this is important because a lot of the things are going to be based on this understanding. There is very little math in this thing, so there is no table whatsoever in this whole lab in here. It's all questions basically based on your observations. The objective is a good idea to leave it toward the end. And in here, it's asking you, at some point, probably, I don't know if I mentioned that, at some point, at least I mentioned for the Physics 10 people when we were together today, you're going to build your own boat. This is my own version of the boat, basically, using paper. Okay? So at some point, you're going to build your own, and you're going to include that as part of your activity, part of your lab activity. So I need to see a picture of what you did. Okay, so the instructions are in there actually, and there is a link to a website that gives you a video on how to do it step by step. Okay, how to build your own boat step by step. Again, this is the first question is, and the grading is again on the rubric. The first question is, explain why a paper clip made mainly with iron. It's actually iron. Where is it mainly? Do I have my paper? Here they are. If you put it in a cup of water, for example, it's going to sink. So this is a paper clip. If I put this one in a cup of water, it's going to sink. Okay. And it has to do probably with the density of the steel versus the density of the fluid. The density of steel of iron is 7.87 grams per cubic centimeter. The density of water is 1 gram per cubic centimeter, and it does not displace an amount of water that is equal, at least whose weight is equal to that of this paper clip. So that's in a nutshell what the answer to that. Now, in the same token, you have a boat which is much, much, much bigger than what the paper clip is in terms of mass, and it's made out of the same material, steel, mainly, okay, will float. So it's not a matter of density. It's not a matter of mass, because the mass of the boat actually is much bigger than that of the steel. It's not a matter of density because most materials have the same densities. So it's a matter really of how much they displace versus their own weight. The boat in this case displaces more water because of its shape, that it basically will have enough buoyancy to stay afloat. Okay? So you really have to have this understanding in here. So it's not either one of these two things, okay? So the same boat, if I probably make it into a paper clip, for example, or a bunch of paper clips, all of them, they're going to sink into the bottom of the ocean, okay? Question 3, can you think of a way to measure the volume of any irregular shape object using the principle of Archimedes? It's a good idea to read this section if you don't know what that is, okay? And there is actually in the textbook, there is actually a schematic of how to do that. So, okay. So all you have to do is basically put the object in a container and then measure how much volume of the displaced fluid. That should be the same volume of the object, okay? So again, this is not a test. This is part of your lab for your understanding. So you should not really have difficulty with this one. If you do, please let me know. Again, the principle is very simple. Archimedes principle, it displaces an equal amount of its own volume. So all you have to do is just measure the displaced fluid, the volume of the displaced fluid. Okay? That's how you measure the volume of objects. Which brings us to this activity now on this link. So I'm going to click on it and come back from the other side. Let me first of all open a new tab in here. Come on. Let me click on it. And meet you on the other side when it opens. So let me stop sharing the PDF file and share with you the open page. Okay. As I said before, the viscosity is in the bottom and the opacity is on the top. Let me see what happened if I change the view in here. So from 100% to, so all I can do in here, for example, on the Microsoft Edge is reduce the view by 90% and I have everything in here. As I said in the intro, the fluid viscosity, you're not going to be touching it, basically the viscosity of the water at room temperature is given, so on and so forth, so you're not going to worry about it. At the opacity, leave it as is. So what the opacity does, it makes the fluid less or more opaque. Basically, is it going to be transparent or not? So put it right in the middle, somewhere in there, semi-transparent if you wish, okay? So that you see your object. Because if I put more density in here on this object, and if I change the opacity to very high, I don't know where the object is, okay? That's the only problem with this property in here. So I put it somewhere in the middle, and let's change this one to that of the wood, because we start with about 0.5 for the wood. The density of the water, this object to about 0.5. Again, during the transition, ignore what's going on. There is a force of drag and so on and so forth. So right now it disappears. So this is basically what you need to do. The fluid is at 1 gram per cubic centimeter, we'll start with. And the object density is similar to that of the wood, depending on what type of wood, of course. If it's a maple wood or depending on the wood, it's a different, they have different densities apparently. So you have to be careful with that. The mass, the volume is fixed at 1,000 cubic centimeters. So if you know the density is 0.5, all you have to do is take 0.5 times 1,000, you're going to find 500 grams. That is the mass, okay? So how to calculate this thing is very simple. Every time you change the density, multiply it by 1,000. You find it in grams. So right now I'm doing 0.75. At 0.75, if I multiply it by 1,000, it's going to be 750 grams. But of course, I want it in kilograms. That's the SI. So it's going to be 0.75 kilograms. If I want the weight, all I have to do is multiply it by 9.8, okay, or 10, approximately 10. So it's going to be 7.35 newtons, okay? If I multiply it by 9.8, by the way, use 9.8 for this lab, okay? Don't use 10. So it's going to be 7.35 newtons. Since it's equilibrium, in this case, the buoyant force is exactly equal to that of the object. There was a question today in lecture for physics 10. Toward the end, basically, we said, okay, a person basically swimming in salty water, well, how would his buoyant force, because the salty water is more dense than fresh water, is he going to be experiencing, because he will feel kind of floating no more, is he going to feel better? No, the answer to the buoyant force is still his own weight. As long as you don't change persons, so the buoyant force stays the same. But at that case, he displaces, basically, he doesn't just need to displace as much fluid as he does for the fresh water to stay afloat. So that's the only difference in terms of the two, okay? But the buoyant force stays the same. In this case, it should be the same. So that is some of the observations you'll be doing in here, okay, for this lab. So let's go back into the wood in here, put it back the value that we should be at. So this is the value where we started with, okay? And I'm going to come back to this one. So I'm going to stop sharing this screen and I'm going to come back to where the instructions are. So that's the link in here. make sure that the fluid density is that of water, namely 1 gram per cubic centimeter, and the object is that of wood, namely 0.5 grams per cubic centimeter, by using the slider above this one. So those two sliders, the one I was dragging in and out, that's the way to change the densities. Note that the volume of the substance is fixed at 1,000 cubic centimeters. So that's not going to change throughout the entire lab. So the volume is the same. So if the density changes, the mass changes. So the object size stays the same, fixed. So basically, is it more massive or less massive? That's the only thing that's going to change. Now it says to keep the viscosity of the fluid low and the opacity in midpoint. So that's basically what I was talking about. This lab focuses only on hydrostatics, meaning that the fluid is allowed enough time to settle. So if you have a drag force, so we'll have to wait for that to vanish, basically. Because it's still in motion when you have drag force. The drag force is proportional to the square of the velocity. So if the velocity is not zero, there is a drag force. So there is a dynamics there. We don't care for that. We wait for the velocity to become zero. That means we reached the basically hydrostatics level. At that point, we don't care about anything else. So this lab focuses only on hydrostatic. Okay. So so we are not concerned with drag forces or transitional behavior, transient behavior. Question 4, verify that the mass of the object, so every time you change the density, it should change. So in this case, it's 0.5. So I want you to make sure that you know how to find the, using the expression that we saw at least for the physics 10 today, and the others probably have seen it last year when you guys took it. So the density is mass over volume. So the mass is density times volume. The volume is given in cubic centimeters. Okay, and the density is actually in grams per cubic centimeters. So when you multiply the density times the volume, you should get the mass, but the mass is going to be in grams, not in kilograms. Okay, so you need to divide that number by 1,000 again to find the answer in kilograms. So a 0.5 gram per cubic centimeter times 5 times 100 times 1,000 is 500 grams. Divide that again by 1,000 to find it in kilograms, because there are 1,000 grams in a kilogram. Then you end up with 0.5 kilograms. So basically, the system should give you the correct answer. If it doesn't, then you need to tell me. Then there is a problem in the calculation. Based on your observations, so this is still question 4. Okay. Did the block of wood sink or float? Of course, you're looking at it. So is it going down or is it staying afloat? So in this case, it's floating for the first question. If it did float, determine the ratio of the sunk portion to the non-sunk portion. So in this case, it's a 1-to-1. Let's go back in here. Stop this sharing and let's go to the other one. The ratio of the sunk is 0.5 V, whatever the volume is, which is 1,000 cubic centimeters. So 500 grams is below. 500 cubic centimeters, I'm sorry, below. Half of it is below. The other half is above. Okay. So the ratio of half over half is 1. So basically the same amount of fluid has sunk and the same amount is still above. The same amount of fluid, the object, is below the level of the fluid and the other one is above it. So that's the answer to the question. So in this case, it's a ratio of 1. All you have to do is take 0.5 V divided by 0.5 V and you're going to end up with 1. If I change the density to a different number, for example, in this case, it did not float. So that part of the question, I don't answer it. So if that's the case, all of it is underneath. But if I take a different density, for example, 0.8, so right now they have a drag. So I'm not gonna do any reading. Wait for it to settle. Then it's telling me 0.8 to 0.2. So in this case, 4 times, because 0.8 divided by 0.2 is 4 times, is below the level, the surface of the water. Okay, 4 times is below, and only 1 in 4, or basically a quarter of the object is above, and 3/4 is below. Okay, no, I'm sorry, it's 4/5 is below and 1/5 is above. Okay, the ratio is straight out. 4 times more is below than above. Okay, so most of it is actually below the surface of the liquid in this case. So if I change it to a lot less dense object, for example, 0.3. In this case, again, I have 0.3 over 0.7 or 3/7 below, and most of it is actually above. So that's the answer to the question. That is provided if it's floating, like in these situations. But if it's not floating, then you can't answer that part of the question. So that part of the question has to be deferred to something else. Let me go back into the questions.
Hey, Professor, I had a question.
Yeah, go ahead.
For the question 4, when we're
I
saying
can't
that,
hear you well. Is it my microphone or? That's it. It's Max. Go ahead. Go ahead. I'm sorry.
can you hear me now?
It's still kind of low, but go ahead. I think I can hear. Go ahead.
What about now? Is that better?
Yeah, it's a lot better. Go ahead.
Okay, so when we're talking about, on question 4, we're saying that half of it is sunk, half of it is floating, right?
Yes.
So we would put the sunk portion is 1-to-1 ratio, and when we say that half the block is sunk and half the block is floating, so 0.25 grams cubic centimeters is above the water, and 0.25
I wouldn't want to go into that detail. All I would want to say is this: in this case, it's a ratio of 1-to-1, meaning the same amount of the object is above the level of the fluid, and the same amount is below. Because
Okay,
0.5 over 0.5 is 1, basically. The ratio is 1 in this case.
I
So
see.
this, okay.
Okay, okay,
In the
all right,
last example of 0.3, the density was actually most of the fluid is still most of the object is above the level of the fluid.
right.
Okay. So that's basically what, and you have to append a number to it, because most is not good enough. You have to get a number in that case, because 0.3 divided by 0.7, so it's a 3/7 of the object, not 3/7, 3/7 of the object is below, and the rest is above. So most of the object is actually above. Okay. Yeah.
Okay, so for this one, it's
So,
fine. Just put it
however
in
you're gonna you're gonna do it. You have the ratio. You have third of the entire volume in that last example is below, and the 7/10 is above. So most of the object is above, actually. Okay.
Okay.
But in another example, I believe it was the other way around. Most of the object was below the level of the fluid than the object that is showing up. Okay. So it depends on the density, depends on the problem. So again, the activity will give you the numbers. All you have to do is just do the ratios and tell me based on that. Okay.
Okay.
That is if it really indeed sunk. If it did, I'm sorry, if it did not sink, if it's still floating, okay? But there is another possibility that the object might sink.
Mm-hmm.
So in this case, it did not sink, so the ratio 1-to-1. If I increase the density higher right now and wait for it to settle down, now 85% is sunk and 15% is above, so it's still floating in this case, okay?
Mm-hmm.
So let's go back into the activities and see where we are. Stop sharing. And let's find where the other one is. The questions are. Question 4. It's still not over yet, the question, okay? So that's part of the question. If for determine, okay? And would you say that most of the object is below or above the fluid? So that's the last part, okay? So you're going to tell me the ratio, and then in this case of the wood, it should be 50-50. I can't tell you that they are most of it in sunk or most of it, actually they're halfway, okay? So that's the answer to this question. Again, what is the value of the buoyant force on the block of wood? If it's sunk, what is its apparent weight? Okay. Now, question 5, let's stop sharing in here. And let's go back into the activity itself. Now, if it's, in this case, it's clearly, in this example point, the buoyant forces from the reading from the table is 8.33 Newton because it's still floating, okay? And it's the same thing as its own weight. Because it has to be, otherwise it's going to sink if the object weight is more. So no matter how much I change in here, the buoyant force is going to always be equal to that of, when it settles down, of course, to that of the weight, okay? Now, if it's sunk, let me take a case, for example, when it's sunk. In this case, look at the numbers. 18.13 is the object weight, but the buoyant force is only 9.8, okay? And the apparent weight is actually the difference between them. the apparent weight in this case is 8.33. I'm missing an n in here. Please add the n in there. It's in Newton. It's a difference, okay? If you don't care about this expression, the normal force, all you have to do then is just take the difference between the object weight, which is pointing down, and then the buoyant force. So you need to provide an additional force coming from the support in here in this case, which is 8.33 newtons. That keeps it from sinking any further. So that is the apparent weight. So the apparent weight is the difference between the two. So in this situation, I am answering the question about the buoyant force because it's sunk now, actually, for this example. Not the first example. The first example, the question to this one is different, okay? So the question in this one, if I wait for it, the 0.85, okay? So in this case, the buoyant force is going to be 0.33, and the object weight is going to be 8.33, and the object did not actually sink. It's still floating, and there is no normal force, actually. It's equal to 0. The object has no apparent weight, basically. It's weightless, okay? At least apparently. So it's floating, okay? So if I bring down the opacity down, it looks like this object is suspended in air, okay? So that's basically how this thing is. So let me stop sharing this screen and continue with the questions. Any questions so far? Everything is straightforward?
So when buoyant force and object weight both equal to 9.8 newtons, is it perfectly balanced? So it's still floating, right?
Yeah, the two forces cancel each other. Yeah, it's balanced. It's
Right.
floating. Yeah.
Just barely, right? Because right afterwards, I noticed that it sank, and then the normal force started going up, which.
If it sinks, the normal force will be up more. Okay, the normal force will be the difference between the two. But
okay.
the 9.8, if both of them are 9.8, then Amanda, to answer your question quickly, the apparent weight is the difference between the weight and the normal weight. And I'm sorry, the apparent weight is the difference between the normal weight and the buoyant force. To go back to the example that Jose was mentioning, if both of them are 9.8, then there is no apparent weight. Therefore, it's actually floating.
So apparent weight would equal to normal force?
Yes, the apparent weight is the normal force.
Okay.
Okay? The apparent weight is the normal force. Is the force you need to keep it basically from going any further, because it's now sitting on a support of some sort in the bottom of the tank. Okay?
So that's the force that you would need to add to the buoyant force in order to
keep it from going further below the level of below the bottom of the tank. That the tank, how much it needs to feel. If you are actually swimming yourself, if you go under the tank, that's how much you feel actually your weight is. You feel less weight. That's why it's called an apparent weight. Because let's say, for example, I weigh 180 pounds, okay, and I go underneath water, okay, and somehow will be standing on the bottom of the tank, okay. My weight is the difference between how much volume I displace and basically the mass of the weight of the volume I displace and that of my own weight. So I probably would feel like I'm weighing only 140 pounds, okay. That's my apparent weight. If I stand on the scale actually will give me 140 pounds, not 180 pounds. If I get out of the tank, my reading again, the scale will give me 180 pounds.
So your apparent weight or the normal force would essentially be like an extra 40 pounds.
No, that would be the buoyant force. Would be the extra 40 pounds. That is basically how much I'm being lifted up by the buoyant force. Because I'm being dragged toward the earth by 180 pounds, but the buoyant force is lifting me up by 40 pounds. So in a net effect for me, I feel like I'm actually being pulled only by 140 pounds. Does this make sense?
Kind of.
Okay.
Yeah.
It's just the difference between the Earth's pull on you and what the water is like, basically like kind of like pushing you up. Basically,
Yes.
it's just the difference. It's
180
minus 40 is 140. So that's what your normal force is, right? If I'm catching on.
That's very good, Jeffrey. Yeah, that's
I
how
don't know.
basically it is.
Yeah, trying to word it differently. Maybe I can help you out.
Okay, thank you. Does this make sense to you now, Jose?
Unfortunately not, but I'm gonna go ahead and keep looking at it.
Okay.
Keep looking at it. No worries.
Okay.
I'll just keep
Are you like me who don't swim? Because I can't swim. I almost died at the age of 17 in the sea, so I stopped from going on the water at all.
Oh man.
So, so I don't know. I mean, I know it in theory most of the time, so I don't know how it feels. Okay.
I actually surf, so I should probably know this too.
Okay. Okay. Okay.
Thank you guys for trying to help me. I'll keep reading it over and then asking questions.
Please, yes, do. Okay.
Yep.
So let's continue with this things in here. Basically, like Jeffrey was saying, it's just a difference, okay, between the two. That's basically, I mean, if you want to do the math and ignore about the concept, the other things. Okay, so we're going to do the same thing now. We're going to change it to ice, basically. They gave you the density of the ice. Don't use 0.94 because the slider will not give you 0.94. It gives you 0.95. That's why you have to use 0.95, okay? And you're going to do the same thing, and there's a quotation in here that I added in there, and that is to ponder about what happened to the Titanic, or at least the people who were thinking that, hey, I'm looking and I see an iceberg, so it's probably not big deal. But you will notice that most of actually the ice is actually underneath. So if you run into it, you're going to be in big trouble, okay? So it's the same question as before, except they changed the density. And the same question 7 is just like the question 5 from before, except now, what is the value of the buoyant force? Again, you're going to look at it, change basically the density to of the object to 0.95 and do the reading and answer the 2 questions. So if you answered successfully 4 and 5, you should not have a problem with 6 and 7. They're identical. As a matter of fact, if you do it for iron, it's the same question, but change the density now to 8, which is the maximum on that scale. Okay, I made sure that that's the maximum that you're going to go to. So you cannot do, for example, lead, which is a little over 11 grams per cubic centimeter, or you can do, for example, even more denser materials. Okay, so that's basically the maximum for this one. And again, question 8 and 9 is similar to the previous 2 questions. Okay, yes, Amanda, the answer is you cannot use 0.94 for ice. You have to use 0.95 because it's closer to 0.95 than 0.90. Okay, so we're using some sort of rounding. Does this make sense? Because if you slide the slider and you are at 0.9 and you say, okay, can I get to 0.94? No, it's going to jump to 0.95. So that's a limitation in this lab, that's all. Okay. I could have changed it to jumping by 0.1, and you will have very hard time trying to zero on it. You'll spend a lot of time to find the exact value. So I just made approximations in here, and that should work. Okay. So, question 10. Now we change the fluid from that of water to that of a little denser fluid, like for example, heavily salted water or different substance altogether. For example, I don't know, much more denser fluid, like for example, swimming in honey. Okay, so change the fluid. Okay. Change the density. Please do not put it 1.5 or 2.5, anywhere in between those 2 numbers. 1.6, 1.7, whatever value that, and jump from the other one, okay? So I change the fluid and change back the density of the object to that of ice. So we're going to go back of the ice now, which is 0.95. Does this make any difference in terms of the ice floats or sinks? Does it sink now or it's still floating? And if it does, basically the buoyant force and as well as the level of sinking, namely, do I see more of the ice now above the fluid or less of it above the fluid? So that's the question that's basically you're going to be doing. So it's easy enough, I think. I believe that should not be hard. I mean, other than if we overcome those technical issues with the normal force, I think this should be straightforward. Any questions before we go into the making of the boat?
Are we still on? We're not on the ice one. We're on the iron one, right?
We did the iron one, but question 10 brings you back to ice.
Oh, I see.
Okay.
Okay.
And changing the fluid. Now the fluid is not water anymore.
Mm.
Okay, so there is the other slider, the one I was showing you.
Mm-hmm. So it would
Okay.
be just bigger, right? Between 1.5 and
Yeah.
2.5.
Yeah. Yes.
Okay.
Okay, Amanda, you're gonna do this, I'm sure. Okay. So there is a link in there if you really are, if you want to see how this works. There is a link in here. I'm gonna click on it and allow. Okay. And let me stop sharing that screen and share with you this screen now. So basically, I took the steps from there to the from there. Okay.
Are you making a steel boat too or no?
Actually, not a steel boat; it's a paper boat. Okay. If we were in the class, what we did actually in the past, and it's a lot of fun, and everybody enjoys it so much. But unfortunately, we can't do this in class. Is we make paper boats, and we have basically cups. We fill them with water, a big, you know, those chemistry basically cups that we use for chemistry. Containers, and we fill them with water. And the competition there is who can put the most of these paper clips without having to have the boat sink. Okay, and it's a lot of fun because then the question is really not as detailed as this one. You'll be given basically paper, and you'll be given minimal instructions on how to build the boat, and you would do it. You build it within the lab time, which is about 3 hours usually. And then at the end, everybody starts to put, and then they record in their data, of course, the mass of the paper clip. They record also the mass of the paper. And the key thing, again, in order to win really, is to make the volume of the boat as big as possible, okay? That way it can displace the biggest volume of water and still does not sink. And that's the trick behind it. And at the end, that's the conclusion. And it's a lot of fun, okay?
Sounds fun.
But unfortunately, we can't do it. So that's basically the next best thing to do in this case, and that is to build your own. And here is the instructions. Actually, there is a video in here if you would want to take. It's not a long video. It's about 2 minutes video. And it shows you step by step. The only thing you have to be very careful is when you take a piece of paper, do not cut it. And try to use the normal print paper. I don't know what's going on with this one. Let me stop this thing for my screen. Apparently it's in the way. Let me stop. Let me remove this background thing and you choose background. Can I do it no background? Where is it? None. Okay. So when you bring piece of paper, okay, an 8.5 by 11, keep it intact. So the first folding and the second folding, and you make so go through the steps, and you might need to do it a couple of times. Are you guys looking at, did I, yes, it's good. So you might need to do it a couple of times to get the hang of it, okay? If not, go through it step by step, and the instructions are in here, okay? So you fold it, and then you fold it one more time, and you make a slight dent in it, okay? And then you bring it down in here. Remember, there are two layers now underneath. So the first layer folds, and the second layer basically folds in the opposite direction. Before you do it, you see, make sure you look at the where you fold it first, and look at it in the back, and you make this 2 dents in it, and then you bring it to the other side. And the last part is actually the tricky part, is when to bring it and make it actually into a boat, okay? And now you have your own boat sitting in front of you, similar to what I was telling you. This is the one I built, basically, okay? And I put it in the tub, actually, not the tub, the sink, actually. It's not that hard, believe me, V, okay? I think if you are, it should be hands-on, okay? Yes, it's for the lab, Taryn. It's for the lab. You're absolutely right, okay? You have to turn in this activity for the lab, okay? I'm gonna tell you about the question for the discussion later. So basically this link, I found it very fun. So I'm hoping that you guys find it easy enough to follow it. No, you don't have to complete it by tonight, okay? You have still, what is it, from today until Friday, not tomorrow, a week from tomorrow to complete this thing. So enjoy yourself. Try to basically get your hands on, because again, we're doing physics, we're doing stuff with hands. We're not supposed to do things online and click mouse and click this and things like that. That's not really experiments. So I'm trying to get you a feel of as much as possible of what we do actually in, have we been meeting in the classroom to actually do these things. So enjoy yourselves. What I will recommend again is to use a print paper. Don't use those papers that you use for your notebook, because those apparently they absorb water and they sink very quickly. So you're going to have difficult time with it. Try to get your hands on a couple of this. That is part of the lab. The other part is actually to take a paper and crumble it whichever way you like, or even put it flat and try to push on it and see which one that experiences the highest, basically, buoyant force. Which one resists the sinking more? And that's the last question, actually. Let me stop sharing this thing in here. So after you complete this activity, you're going to answer the question based on your observation. Does the shape, so this is based on your own observation. I can't tell you how it's going to go. Play a role in whether or not object sinks or floats, okay? So based on what you do, finally, you're going to put the conclusion here. Don't forget that you're supposed to put an intro in here, okay, for this one. And then at the end, this is basically what I did. Like I said, this is the one I built myself, okay? And it's floating. I put it on the sink and took a picture of it, making sure that it's floating. Push it, try to push it, and see, try to compare the two, have a feel for it, and then submit your picture, okay? So your picture actually is graded, and there is actually in the rubric how much you're going to get points for it. So please make sure you submit the picture of for the lab. Otherwise, you're going to lose points in there. And everything else is graded the way it's supposed to go from there. Okay. And
do you want us to submit it like on water or just like wherever, the picture of the boat?
I would rather have it on floating, okay? I would want it to see floating.
Okay.
Either on a bucket or, for example, like I did in the sink, basically make sure that it's stopped and that's it. It's going to work, okay? And I didn't have a lot of water, honestly, there. I just had a little bit of water. It didn't go all the way up, okay? So you can do, okay. I guess the discussion points in here is going to be on Archimedes Principle, okay? Archimedes Principle. That is basically how to measure. It's the first question in there, okay? Or which one? It's the third question in here, okay? So that is the point of the discussion today. So I want you to really come up with a way of expressing this one in your own term, in your own words. This is it. This is the entire lab. I thought it's kind of short, isn't it?
Yeah, it's short. It's easy. Looks
okay.
easy.
Okay. So again, if you have any questions, please let me know. Very good. I'm glad that it's fun too. Okay. So at least try to answer the questions and do these things. I know that you might have difficulty with the GeoGebra basically when you go to it, and that's because of the resolution on the screen. Try to change the view there, basically on the screen on the website from, let's say, 100% to 90%, probably is going to bring everything into view. You're not changing anything from the bottom. So if you don't see them, just leave them the default values. They should be fine for you. The opacity and also the viscosity, okay? You're not going to be changing those. So if you don't see them, don't ignore them. The only thing that matters for your lab are actually, first of all, the object density, the fluid density, and that text box that basically give you all the data. Even the diagram, the force diagram, is irrelevant, okay? Unless you guys have any other questions, I'm going to basically stop the recording and keep the session open for anybody who wants to stay open here. If not, the discussion again, has to do with Archimedes Principle. You're going to put it in your own words, basically, giving me an idea into how you think we should measure volumes of different shaped objects. I know it's a mouthful, but that's basically the task.
So basically, talking about Archimedes and about the like just how to go ahead and find the volume.
Yes, of any object.
The principle of Archimedes?
Yes.
Okay.
Which one, Taran? I don't understand. Spell what? Yeah, okay. Archimedes is they gave you.
Okay, this is related again to the discussion.
Aha.
Basically, it's like just the text box, right? That's the discussion, the one that's in the lab, or you
Mainly,
want
yes. Yeah. But I want you to formulate also the principle too. I really want to see an understanding of what that principle is. Okay?
Gotcha. Okay.
Okay, guys. If there are no other further questions, like I said, I'm going to stop the recording and keep the session open until the last person leaves or the time runs out. There is no lab due tonight, Daniel. The lab is due tomorrow. Is it due tonight for the previous lab? It says October 1st. Are you serious? Okay, let me check that. That's serious. That's not good. I thought I changed those things a long time ago. Okay, let me check it and fix it if that's the case. Oh, you're right. That's not good. Thank you for... Huh. You guys need to tell me that ahead of time because I made a promise last time around and hopefully you hold me to it. So if you don't see it, let me know immediately that something is wrong so that we don't have to worry about it to the last minute. So it's going to be the 2nd, October 2nd, which is tomorrow. Okay. And it's going to be Friday. I'm sorry about that. Okay, guys. I fixed it, Daniel. Thank you for bringing it up. And everybody else, please, when you see something like this one, you let me know. Every lab from a long time ago, we said that it has to be done, not on the day when we actually have a lab, the day after to allow you to make sure you come to your lab, the one that is current, and you have time to finish it by the day after if in case, because I noticed that some people would want to take off so that they can do their previous lab. Okay. So I'm going to stop the recording now. Yes? Good?
Yep.
Okay. Very good. So